You hear me?
Yes.
Maybe sitting far in the back and all things.
Well, thank you, my dear. So,
Hello, everyone. This is a meeting of the Royal Astronomical Society of Canada's Victoria Centre. So, are there any new people here tonight? Well, at any rate, welcome. We've got a great speaker tonight, but we've got a bit of business to deal with here, but it'll go shortly. So, let me step through it. So, we're going to have our regular announcements and upcoming events, and then Dr. J.J. Cavallars will be talking about exploring a new world at the edge of the solar system. After that, the coffee and everything, after the presentation, we'll have coffee and tea and cookies in the fourth floor lounge at the Elliott Building, and everyone's welcome to go up there. But announcements first. I'm your fledgling president, and the shakedown continues. The main features that we had since our last meeting, the mini AGM, is that one, we had a telescope called the Ray Bryden telescope, which I really didn't know very much about. I know a lot more about it now. And the main thing is it's very heavy. And we had 5 early men show up, and we even recruited another person named Kelvin, who's part of the FDAO, to help us lift this and put this telescope on a beautiful mount that was I guess you'd call it a set of casters that was fabricated by our very own Sid Sadhu, and it worked beautifully. And we had to roll it out of the museum because we are actually putting new carpet in the museum. They are putting new carpet in the museum, and that achievement occurred, and we're very pleased with it. Since the last meeting, a number of us, Nelson and Bill Weir and I went out to Astrofest in Nanaimo, and I wrote about it in our latest President's Message, and it's also mentioned in the newsletter, so I won't talk more about that. And then a few other things that escape my mind right now. The Vice President doesn't have much to say. So there is no Vice President right now, but that can change. If you're inspired this evening, please come in afterwards and we can arrange it really quick. Sky News editor, Bruce.
So just handed out a few more hard copies of the latest issue. Interview with Joe Carr, as promised, the article on Besto Slifer, much forgotten about for all his accomplishments. And of course, the crossword puzzle. And gonna be having the next one, probably in a few weeks, we'll have another one coming up. Might be the crossword puzzle. Maybe even the answers to this one.
Answers, that would be handy. Well, thanks very much, Bruce. Bruce is doing a great job with the Sky News newsletter. Now, I was contacted by a name called Bob Duhamel, and he has been going through various club newsletters and putting out a Reader's Digest of them, and it's at a thing called amsky.com. And basically what he's got there is quite a nice newsletter, and he's compiled a whole pile of things with the various clubs on the left. And if we go down here, there is one for Sky News. Sky News is in the list. There's 3 Canadian newsletters being picked up on this thing, and we're one of the 3. The other one is, I think, London, Ontario, and some group from Hamilton that's not associated with RAS. But at any rate, they have a thing here for, click on that, more articles. And it shows you the articles that we have, and he's got the page number that the article occurs on, the author, and we're on the big leagues now. We're being, a lot of people can pick us up. Yes, sir.
He actually has contacted me, wanted me just to let him know when I was issuing. I had some concerns because I couldn't get a definite idea whether he was gonna ask for a pay at some point. And I didn't want to give permission by sending him stuff or letting him know stuff, because that would be considered at some point to use our stuff without asking us. So there's a little bit, he looks like he wants to get into the pay.
Okay,
So I kinda,
yeah, he has requested, he's sent out a position paper to me. He's thinking of charging $1 a month for his thing. Now, for us, we have a coveted guide here called Explore the Universe Guide, and we're selling that off, and we're making 8 cents a copy. So I don't know, $1 a copy sounds outrageous to me, but at any rate, I think it is something that gets our name out there, and I don't have a problem if we have to kick in a bit of money as a club to help him out, but he doesn't seem to be like he's a gouging to me.
he was also publishing and then asking permission. That was the other problem I had for him. So he was posting club member pictures for his cover picture for his website without asking permission. So that I had a problem.
He probably didn't ask you, he asked me.
No, yet there were other people. He posted David Lee's picture without asking permission.
No, he asked me about it.
Did he ask permission after the fact?
No, he asked me.
It seemed like it was the
Yeah, okay, so I think he's pretty respectful, and David Lee's beautiful lunar eclipse sequence was on one of the pages for the month, and I think it's a win-win situation here, so and he seems to be pretty out in front. So, at any rate, we'll move on from there. Treasurer, Deb.
Yeah, I just want them out. Not that it's convenient, I didn't have all the checks I wrote tonight. For our gaming, it's still at $20.09. Members account is $14,286.17. And under the following verses tradition, please cash your check.
Already done?
Okay, thank you.
Thank you. Chris, membership?
I'm over here too. Our current membership is 279 members. They are attending the race group.
Thank you. Okay, Astronomy Day team captain, David, do you have anything to add?
Yeah, anyways, I want to thank everybody who's sort of volunteered, and we still can use a lot more volunteers. Please come forward and let me know if you're interested. We've actually, for each of the activities, we have a lead now for each of the activities, so you'll already notice that I sent an email to everybody so you can see who the leads are. If you're interested in a particular area, please contact them. Otherwise, contact me, and then I'll put you in touch with them. I think there's still going to be setup and breakdown activities that I haven't mentioned yet. So if you don't want to be there during the day, you can maybe help us set up and then break down. I don't know if anybody else is collecting volunteers for the evening, but there's always tradition of bringing up at the center of the universe on the same day. So I think if you want to make that known, you can go up and do the same thing.
Is the same list of volunteers from last year, or just going to ask you about that, or should we register? They have a list of the date for 5 o'clock early to set up.
Right.
So does it carry over?
It will be. I'm going to refresh it.
Yes.
So I will.
Chris, I get the leads.
Sort of.
Okay, good. Good. So, yeah,
On
so,
that part, yeah.
so if you're interested in volunteering to see you can then see this. Other than that, thank you for all the great efforts. I think it's going to be a great astronomy day.
I'm really excited. I'm very happy with the great job you're doing organizing it, David. Thanks very much for that. Schools program, Sid.
We were supposed to be taking last night we had a most exciting evening thanks to our weather person. He somehow respectfully arranged a beautiful 2 hours window for us to look at different things in the sky. And I would like to acknowledge a number of people who helped out in spite of hailstorm. I have come that thick hailstorms on the road. The cars were just going everywhere, here and there. But anyway, we managed. When the time came, thank you very much. It's just the sky cleared wonderfully. Here is a number of people I would like to thank for coming over. Bill, Weir, Diane, thank you very much. I'm glad you found your.
Yes,
spare part.
yes, indeedy. I'm glad to.
David Lee, Chris, thank you for coming. And Reg, of course, he was there organizing the crowd. He did a good job. And also, I think we should talk about of giving away some tickets.
Oh, yeah.
Free tickets, yeah. Alex and Michael Wheatley, thank you for coming. The rest of the people who volunteered for last night, I called them as I saw the rain coming down, hailstorm coming down.
Not to come, so.
Stay home. Well, I'm glad I told you stay home.
Well, we left home in the rain, observed us at the DAO where our story, so it would have been personal.
Anyway, it was a great evening. Thank you.
Okay, did you mention Scott?
Thursday,
Chris?
tomorrow, could you do the same magic please for tomorrow?
No, only one that mentioned I might.
We are supposed to be the Wishers Elementary School, so we'll see.
So this event occurred at the Millstream Elementary School, and you can see the astronomers out there. Early on, through divine intervention, the skies parted, and we had a beautiful view of the moon. And this was really special because the part of the moon that exposed the Sea of Serenity and the Tranquility, Sea of Tranquility, where Apollo 11 landed, that was visible through all of the scopes. And there was a contest that was arranged. It just all lined up pretty well. They gave 4 pairs of tickets to the movie Apollo 11, which just started on the. See. At any rate, Apollo 11 is a movie that is made from old footage that they found sitting in a warehouse in Florida. And it was 70mm film that nobody could really do anything with, and they've just done a terrific job doing this. And the movie is at the Capitol 6 Theater. If you've never been there, it's the most comfortable theater with back chairs and everything. But the Rotten Tomatoes, the audience gave it 91% favorability. Critics, 100%. I've never seen 100% before. It is a stunning display. So please give it a thought. It was really great. It's all lined up with this trip, and we could see where it landed and the other night, and kids were all excited. So it was a wonderful evening. Let's see. So technical committee, Matt.
No good news to report. There's been a computer malfunction. Don't know the exact cause. It coincided with power outage. Thought we had done everything we could to protect against surges with 2 layers of protection there, but apparently not. I think Joe may have mentioned that he was donating a replacement unit for us, so we'll get that to good use soon. The other major file is still ongoing, being the collimation of the TPO.
Now, you received another instrument for it. Might help with that, too.
It has been put to use once. I haven't gotten a full briefing on the events of that night, but there was no sudden win with it. It'll be revisited.
Yeah. We should say one of our colleagues, our cousins from the NIMO came down with his no, not Nanaimo, it was from the Comox Valley, with his device to try and collimate. And he had the same one we had, and they both gave the same results. So they're both functioning the same. I think that's a step forward. So at any rate, keep at her. Good luck. Website, Joe?
Website is functioning as it should. I don't see anything wrong with it. If anyone has any comments, let me know. Obviously, email lists are part of the game, as well as social media presence. So if anyone has any feedback, please let us know. Thank you.
Okay, thanks. Michelle is not here with the derby, but I should say that Michelle and Dan Posey did a terrific job organizing the class to the derby session. And the mix that night were myself and Sherry Butner, and we crashed her party, and we had a great time. We had 19 people up there, and it was a beautiful night, and we had a lot of fun. So, but they did a great job setting that up, and there's going to be some imagery that he has downloaded. It goes to a file server, and he will be able to distribute this shortly. So if you're interested in getting any of the files for processing, please contact myself or Michelle, and we can make it happen. National Council, Nelson.
Yes, there has been another meeting of the National Council, of course, was held in February. The next meeting, I think, is going to be at the PA. But the principal items that were discussed at the February meeting of the National Council, this is a WebEx kind of thing. And the first issue that keeps resurfacing is how the sky news ought to be treated. And I suspect this is in terms of tax treatment. One, should it be acknowledged to be a loss leader set out to get people interested in astronomy, or should it be a member benefit? Each one of these has, I guess the third thing is that it would be what the member benefit means that it would be given free or included in the membership. And I'm not sure exactly, and I don't think anybody has been dealing with this, exactly what the consequences of this are, but it always seems to come out for discussion at the National Council, and it will be discussed again at the PA. The robotic telescope, another thing that came up was that the robotic telescope in California has been getting a fair amount of use. The principal item that was discussed is whether or not it ought to be insured. As I recall, this thing cost about $150,000 to erect, and it is not insured. But apparently, it would cost a fortune to insure it. That remains an item that will be discussed in the GA, I believe. Probably the most important thing that was discussed at National Council, and this is something that Chris has probably admired and continually, is who ought to be on it. Because there are lots of people that appear at the meetings that are not listed as national representatives. They just appear at the meeting. And when they do that, they vote. So the issue that is discussed is who ought to be a member. Are people that just show up that aren't national reps, are they members? And should they be allowed to vote? And Chris has a couple of, I guess you could call them adversaries in trying to clean this up, which Chris is trying to do. And there are people that resist it because they come to the National Council meetings, although they are not members, and they vote, and they influence what the National Council does. So that will be something else that is discussed today.
Eddie?
That's it.
Why are they allowed to vote?
Thank you.
Well, you sort of have to envision this taking place. What you're looking at is a screen with a bunch of pictures on it. This WebEx presentation. There will be an array of pictures, and throughout the meeting, the pictures vanish. So you can't tell whether the people there,
Maybe I should make a couple of comments about that.
please.
Okay. Just National Council, there's sort of a discussion about who should belong to it. Like each center sends representatives. Sometimes the rules are kind of applied rather loosely. There are people who, in theory, there's like a term limit that you can't be national rep for forever and ever. And there's one or two people who might meet that description. And then there's also a question of whether committee chairs should be should have a vote in national council. So we're kind of, letting national council sort that one out because the board kind of has enough other issues to deal with. Just briefly on the Sky News, that's not the terrific one we were talking about here, but the other terrific one that comes out of Toronto and or wherever it comes out of. Actually, the editor is Gary Saronic, who's in the Okanagan now. Used to be around here. It's a very challenging time for publications right now. Sky News is not making money the way it used to. And so we were thinking of kind of changing its relationship with RESC. Right now it has a separate board that runs it and all that, but it's actually wholly owned by the RESC, and there's some discussion about bringing it right into RESC and changing it around a bit to make it more financially sustainable. Just while I'm on the subject of publications, I don't know if everybody heard this news, but this week the company that owns Sky Telescope went into Chapter 11 bankruptcy protection in the United States. Now, it's a company that owns all sorts of publications from soup to nuts. So I'm not sure whether this says that Sky Telescope is losing money, but I've got the impression that they have had some financial challenges in recent years. And so anyway, they are probably going to be sold, and I want to scotch any rumors that we're going to buy it. But anyway, this gives you an idea of what's going on with some of this stuff. But yeah, Sky News and probably the Journal of the RESC, we really have to look at those and try and make them a bit more sustainable going forward. And a lot of publications depend more for their income now, for example, on their websites, which is kind of a thing that drives readers both ways, and so we're working on that. So anyway.
Chris,
Yeah.
do you think if Sky Telescope, for example, were to vanish, would that be a good thing for Sky News in Canada? I mean, obviously, we might get some business out of it.
At first blush, it wouldn't be, because the Sky Telescope actually sells a lot of our publications, through their sales division and on their website. So we would actually take a hit. But in the longer term, that's actually a very good question. So. And we actually make a lot of money from U.S. sales, and with my RESC hat on, I smile when I see the Canadian dollar is down, because it means we make more sales in the U.S.
Okay, thank you very much, Chris. While we're speaking of sales, I'm a very unsuccessful salesman for Explore the Universe guide. When I was up at the Astrofest in Nanaimo, I sold 3 copies, and I was quite pumped up about that until I found that Nelson sold 10. So Nelson is your closer. He's pretty impressive. Yeah, I've got some copies here tonight. They're $12 each. If anybody is interested in buying one, could they see me after the show? And that's the end of my sales pitch. We're very excited about our speaker tonight, and in fact, Dr. J.J. Cavallars, when he's ready, he can come down and set up his display. I'll introduce him while he's doing that. He received his PhD from the Department of Physics at Queen's University in Kingston, Ontario, and he's been working at the Dominion Astrophysical Observatory in Victoria for nearly 2 decades now, and is a member of the Canadian Astronomy Data Center. Now, basically, the interesting thing with JJ is I asked him for a biography, and he didn't give me one. So I had to go onto the web. And last night I was talking to Scott Mayer out at the Moonfest out at Millstream Elementary School, and Scott said, I'm really interested and excited about JJ's talk tonight. And I said, well, you know, I had to dig around for it. And I came across this terrific columnist article on February 17th, and it described about JJ's trip back to the East Coast for the Ultima Thule big New Year's bash. And he took his wife, and his wife got a spiritual dress and everything like this. And they went to the place, and it turned out to be not a lot of music and stuff like that. It seemed to be a bunch of presentations, of PowerPoint presentations on science data. Well, it just turns out that the person who wrote that article was Scott's wife. So that's just amazing how this all fell together. I hope I haven't spilled too much stuff. It was on the public domain. So
Yes.
I'm going to turn it over to you now, JJ, and we'll try and hook you up with a microphone.
Great. Thanks very much, Rich. Thanks a lot. Hi, everyone. I'm going to start off. I'm going to make it a little bit reminiscent of our New Year's Eve celebration here. So here, does the audio work for this?
Oh, wait a second.
Very becoming.
Okay, so while Jen's passing around, there's some 3D lenses for you there. Let's see if this works now here. Oh, let's get the audio coming through here. Oh well. Maybe this way instead. This was. So we had a pretty good rock and roll kind of New Year's Eve party, even though there was full of lectures. Because we started the kind of New Year's Eve celebration off with a debut from Brian May of his New Horizons single. So what he did was he composed this piece of music to kind of reflect the feeling in the atmosphere of the exploration that had taken place at New Horizons. You can watch this on YouTube. And it was not your ordinary science lecture. So, there were a lot of people having a lot of fun. And it was a real New Year's Eve party. And of course, there was a bunch of people who were stunned by what was happening in the data analysis room. So anyway, this kind of, you can watch this on YouTube. It recounts the encounter with Pluto, and then on past Pluto, which is pretty exciting. But then the real mission was about going on to MU69, of course. So I'm going to stop that. Okay. Let's see here. Okay. Great. Okay. So, I want to give a little bit of context for what happened with Ultima Thula's encounter, but I really don't want to dwell on it too much. I want to really talk about the exciting results that we have. So I'm one of the co-investigators on New Horizons. There's about, I can never really tell for sure how many people in the room, but there's certainly more than 25 and less than 50 co-investigators on the mission. And there are people from China, from India, from Germany, Canada, the United States. It's quite a diverse crowd of people working on the mission. All of their activities, though, that are sort of focused on the actual New Horizons itself, are funded by NASA. This was a fully NASA-funded mission. There were no international space agencies that participated in funding the actual mission itself. So let's just talk a little bit about the spacecraft. So this is New Horizons. It's been in space since 2006. You saw the launch there. It's a video. It has on board it these instruments here. It looks like there's 7 instruments, but there's really only 4 because some of them are paired. But there's Lori, which is the one that we'll look at a lot of the images for. Oh, thanks a lot. You're looking at a lot of the some Lori images, which is the high resolution imager. It's a little telescope that's sitting right here, and is just a few inches across, right? I mean, most of you have a bigger telescope than this in your backyard. And it's really where all the science data comes from. Then there's Ralph. This is with its cap on, the Ralph imager, which takes color imaging. There's Alice, which is the ultraviolet spectrometer, and Rex, which is the radio. So this is an experiment, or it's a way to communicate with the Earth. It depends on how you want to think about the Rex antenna. So the solar wind folks have a little solar wind detector down here and a particle detector here, which were super fantastic pieces of equipment to have for the Pluto experiment, because we actually were able to detect Pluto's atmosphere. And they're continuing to operate to kind of probe the solar environment. And then finally, not shown here in any detail, stuck underneath this thing is something called the student dust counter. And I was talking about this instrument at the observatory last week, and people thought that the word student was like kind of like there's a thing in stats called the student t-test named after Dr. Student, who came up with it. This is not Dr. Student's dust counter. This is a dust counter built by university undergraduate students. That was part of the whole mission, was to try to have a real public outreach and a real engagement with a new generation of scientists. And so they built the student dust counter. And I'm not going to talk about any results from the student dust counter because we're still trying to understand the signal that's being received from that particular piece of equipment. As the PI for the mission says, there's things on it that you would do differently now that it's been in space. But it was a real learning experience for the students who were working on Okay, so here's what happened, right? We launched in January 2006 off the Earth. It was the fastest launch of a spacecraft in history at 24 kilometers per second off the Earth. And with very little gravitational assist off Jupiter here, a little tiny little tug, and then zoom out to the Kuiper Belt. And so 2015, 2008, so that 9-year journey to get up to Pluto, that's basically as fast as you can do that. Okay? So New Horizons was built light, was put on a gigantic rocket, and it was sent into space as fast as you could ever do anything to get to Pluto as quickly as possible, because there have been many, many, many attempts to get a mission to Pluto, and they kept getting derailed. And the science team was really concerned that by the time they got to Pluto, it would be a frozen world as it was moving farther and farther from the sun on its orbit around the sun. So the idea was to encounter it here when it was close to the sun instead of out here when it's pretty far away. And then out to some yet unknown Kuiper Belt object at the time of launch. So in 2006, right, that was only a decade after the first Kuiper Belt objects were discovered. So our knowledge of the Kuiper Belt was pretty much, zero with order. We knew that there were things out there. We didn't really know how much material there was, what the distribution of that material was, where there might be something you could go and look at. And so a big challenge for the entire mission was to gather enough knowledge of the Kuiper Belt in time so that we could search for and discover something that you could visit with a spacecraft before the spacecraft got there. It was an incredible challenge for the whole trip. So this is an artist's conception of the Kuiper Belt from 2005 or so, 2005. This is the actual Kuiper Belt. This is a plot made by Wes Fraser, who's now back at the observatory. And what we have here is these dots here are Jupiter. There's Jupiter. There's Saturn. Uranus and Neptune. This line here is the trajectory that the spacecraft's going to take. And these little dots are all the different objects in the Kuiper Belt that we know of today. And so the purple ones, there's these purple ones here that are Pluto-like objects that are in resonance with Neptune. That's Pluto itself. Then there's these cyan things, which are what we're going to call cold classical Kuiper Belt objects, or classical Kuiper Belt objects. They're really what the Kuiper Belt was thought to be before it was found. And then there's these red things that are on really scattery kind of orbits going all over the place. And I think this is a video. Let me see here. No, okay. Anyway, it just kind of evolves around so you can see what's going on. Okay, so here we have Kerberos, Hydra, Nix, and Styx. These are the small moons of Pluto. And I want you to kind of remember what they look like. This is New Horizons imaging of Pluto as it flew past and Charon. So you can see this nice family portrait that was taken of the Pluto system. You can get an idea for the kind of resolution you can get from New Horizons as you're flying along. Right? Okay, so these are small, multi-kilometer sized objects orbiting around Pluto. Little kind of proxies for Kuiper Belt objects. Okay, so this is definitely, there we go. So this is a little put together of a montage of the actual imagery that you get flying over Pluto, and then done in 3D using the altimeter data, or the stereoscopic data, sorry, to kind of get a sense for what Pluto looks like. So Pluto's got this amazing terrain. This is not in 3D, sorry everybody. It's a regular little 1D movie, 2D, sorry. You can see these beautiful mountains kind of popping up here, right? I mean, it really is this diverse terrain that is a world unlike our own, but yet somehow similar. These features here in the ice glacier area, you see these kinds of features in the tundra of Manitoba, for instance. In Manitoba, you can see these. These are mountains. These are not rock mountains, though. These are water ice mountains sticking up out of the Lake Glacier. So just run through that one more time so you can see these deep canyons. this beautiful, beautiful terrain of Pluto. I mean, this is just really spectacular. And this was all put together using the imagery that was taken over the course of a few hours as the spacecraft went past at about 14 kilometers per second, going past Pluto. So just a remarkable, beautiful imagery. These lovely impact basins where we can see the impacts onto the surface of Pluto from small bodies that were like Kuiper Belt objects that smack into Pluto now and then. It gets hit by a few objects in very recent history, but this glacier refreshes very quickly. As you can see, there's a real lack of craters on this glacier surface, so that the impact rate is actually quite low. It's rather surprising to see how few impacts there were. It tells us that there really aren't very many small Kuiper Belt objects, very small objects out there. Because if there were a lot of small objects, they'd be running into Pluto and you would see them scarring the glacial surface. I draw your attention to this because one of the real outstanding results from this fly past Pluto was to recognize that there just aren't that many small things in the Kuiper Belt. And we were just starting to learn that that was the case as we were coming up to Pluto, about 2 years out. And we were trying to find something to go to after Pluto. And what we were realizing was that there just aren't very many small things in the Kuiper Belt. Way, way, way fewer than people would have guessed 3 or 4 years before that. And our knowledge was basically evolving as we were looking. And so people were saying, okay, if I do a search and I look for small things, I should be able to find something about 40 kilometers in size. There should be enough of those. I should be able to find something in the direction the spacecraft's going, and I should be fine. And we looked and couldn't find anything. And then we, a classic kind of physics experiment, say, well, maybe we do the calculation, change some numbers. Oh, we should have gotten to 30 kilometers. And so you look and you didn't find anything. Okay. Well, maybe we should go down to 20 kilometers then. And really, you have to get down to that sort of 20 kilometer scale before you finally were finding something that we could actually encounter. And this was a real confirmation of that. And that lack of small things is a really important part of the story of planet formation that we'll come to at the very end. But the fact that there were very few small craters is extraordinarily controversial in terms of the scientific community, okay? The publication where we said this is the number of craters on Pluto's surface as a function of size. Okay, you, sitting in the audience, can look at the image of Pluto, and you can see how many craters there are, and you can count them, and you can see there aren't very many small craters. This is not hard to do as a physical laboratory experiment. It took 2 years to get the paper accepted for publication, arguing with reviewers about what it might mean that there were so few craters. And that paper was accepted about 2 weeks ago. Yeah.
Is part of that due to the fact you have Charon and Pluto tightly locked to each other? Would that keep it away from that primary?
Reviewer number 2.
So it would be protected for a large extent.
Right. So we did simulations to show that, yes, there is a bit of shielding of one object from the other, but it's not substantial enough to explain the dearth of craters. And it doesn't provide a size sorting. And so it doesn't remove small impactors preferentially to large impactors. And so it doesn't modify the frequency distribution of how many small things there are compared to how many large things they are. But that actually was exactly one of the things that we had to address in this manuscript, was demonstrate to us that this was not a shielding effect from one plane to another. Yeah. I demonstrate, there's all, okay. Here's another, this is a kind of a still, but I bring this one up because another fantastic result. So you see the glacier, you see the ice rocky mountains here, and then you see this beautiful haze layer in the atmosphere of Pluto. And the haze layer has some thermal inversions in it. It has a huge amount of structure, and if you look really closely, you can see little curls of atmospheric turbulence, maybe not quite in that image, but you can see the turbulence in the atmosphere of Pluto as well. So there's a really complicated atmosphere of Pluto. And this debate's kind of over, I suspect, in the scientific community of what a planet is. But I'm showing you an image of an object that has glaciers, mountains, an atmosphere, canyons, has evidence of erosion from liquid motion on its surface in the ancient past. Distinguishing this from a planet would be very difficult in terms of what you want to call a planet. So anyway, this is kind of a part of the video. Okay, so that's the goodbye to Pluto. And again, you can see this beautiful haze layer in its atmosphere. Of course, the atmosphere is incredibly thin, right? I mean, it's thousands of times thinner than the Earth's atmosphere, hundreds of thousands. Still, it's there. And you get this refraction of the blue light from the sun coming through. And you can detect that. Okay, so what to do next? So, right, basically, as the Pluto data was coming down and people were starting to analyze it and understand it, we submitted this proposal to NASA and said, please give us $100 million so we can go look at something else. It wasn't really a complete, given that this would happen. But we had already found at this point the target you could go to. It was found in 2016, or 2014, sorry. The encounter took place in 2015, and in 2016 we applied for funding to extend the mission. And we were actually awarded an extension of the mission. It was an interesting award because this proposal contains within it different kind of like levels of things you could do, right? It's like, your basic mission, your moderate mission, your advanced mission, your super extended great mission with all kinds of supporting stuff. So NASA actually approved the super great mission with all kinds of supporting stuff, and then gave the budget for the basic mission. It said, do this, but with this money. And so the mission has actually struggled a little bit because we have to pay for things like the Deep Space Network to uplink and downlink. We have to pay for a huge number of engineering staff to keep the spacecraft operational. And all the extra stuff that we wanted to do was all about training new scientists to work in planetary science and understand how the Kuiper Belt works. And that's really where we thought that would be the legacy, basically, of New Horizons, would be this generation of young space scientists who would be able to do stuff. And it's been really hard to fulfill that part of the mission. We're working on it to try to do so. Okay. Oh yeah, so then actually right there on the project book though, I love this. This is my figure of what the Kuiper Belt looks like, constructed using data acquired in the Canada-France-Hawaii telescope between 2003 and 2007. So well in advance of the knowledge that this kind of mission would exist. And turned into a model of what the Kuiper Belt actually looks like. And that is the model that was needed in order for us to know where in the sky to look to find this target, 2014 MU69. So without actually having started in, there's also, the number of coincidental things you have to have happen. So the Canada-France-Hawaii telescope, the French members of that facility wanted to put a new large field camera on board the telescope to take the widest field images ever taken in order to try to understand the nature of the expansion of the universe and to probe the structure for trying to figure out where dark matter and dark energy are. That camera was somewhat controversial for the community. It was built, it was put on the telescope, and one of the bargains was that if it was going to go on the telescope, it had to do a survey, and if it was going to do a survey, it had to combine together a bunch of science fields from different parts of the community. And the Kuiper Belt study was one of the things that was selected. It's an interesting kind of part of the whole science problem. It was selected in 2005, but the camera didn't work as it was expected to work. And by 2005, we realized that the megacam on board the telescope doesn't work quite as well. And so we had to re-partition the resources, and the Kuiper Belt component of the project was pushed off to the side in favor of some other parts of the science mission. In 2007, or 2000, putting my days right here, I think it was 2007 or 2005, we restarted. And so by the end of 2007, we actually had a very detailed map of the structure of the Kuiper Belt using that camera. So it's kind of all this kind of little fadey things that come along. And that was to produce this map, which I have another image up here, that lets us know what the structure of the Kuiper Belt is in detail, and that there should be something right there for us to find. What was interesting is that it turns out the Kuiper Belt has a bit of a warp to it, and as you go out, if you're just looking in what would be the regular gravitational plane of the solar system. As you get out to the Kuiper belt, you have to actually go about a degree off that in order to really see the highest density of material. The whole problem was that everyone had been looking in the lower density region because we didn't have the detailed model. Once we have the detailed model, things were good. Okay, so here's what we're going to try to understand. We're trying to understand planet formation. So this is a scientist's map of the Kuiper belt. This is the same major axis, so that's the mean distance the object is from the sun. So Neptune's mean distance from the sun is 30 times the Earth-sun distance, 30 AU. There are all these objects. Each one of these little dots is an object in the other solar system. So these things are scattering off of Neptune. They're called centaurs. They turn into comets. There's objects out here that are slowly scattering off Neptune and coming out to be here. There's this group of objects right here that are in resonance with Pluto, with Neptune, the way Pluto is. And there's Pluto in that group. And then there's this group down here that has very low inclination orbits in what we call the cold classical Kuiper belt. The reason we call it cold is because the orbits are not very, are very circular. There's not a lot of non-circularity to the orbits. So when they encounter each other, they do so at very low velocities. And that's kind of a physicist's way of saying cold, low random velocities. Okay. So here we have it, some sort of stats on what's going on with the mission. So the target turns out to be about 80 times smaller than Pluto. We're going to fly 4 times closer. So we need huge precision. The navigational precision that you need to get there is incredibly high. But we only discovered the target in 2014. So normally, Jim, I remember I gave a lecture, I gave a seminar at the observatory about a newly discovered object about, it must have been a decade ago now. We had just discovered this object, 2008, I think it was. Anyway, it had an unusual orbit that would take it way far out of the solar system and back. Completely impossible to explain using any known dynamics at the time. We've been observing it for about 3 months. And Jim said, how can you guys know if you orbited this thing 3 months and be talking about its 10,000-year orbit history with that small arc? It's just kind of a weird scale to get in your head. So here we have an object which we discovered in 2014, and we want to know where it is to within plus or minus a kilometer in a box in the other solar system 4 years later. It's going to have moved in its orbit in the 3 years after discovery. It'll have moved about 1% of its orbit around the sun. This tiny bit of its orbit, we're going to do lots of math to try to figure out exactly where it is. When this was discussed during the initial telecons, myself and an astronomer at the observatory, Stephen Gwynn, who does a lot of astrometry, we muted the phone because we could not stifle our incredulity at the task at hand. That this was actually going to, that somehow this was going to be achievable seemed completely impossible. But, well, we tried. So we didn't know what it was going to be like out there. It's incredibly dark. The reflectivity of these objects in the outer solar system is something like about 10% of the light that strikes their surface reflects back to us. Okay? So it makes dark surface. We only have a few hundred watts of power on board, and it takes 12.25 hours to get a signal from the Earth to the spacecraft and back. So you're not doing any on-the-fly modifications. Okay, so we managed to do that. We figured out where the object was to enough precision by a worldwide coordinated effort. There's a satellite called Gaia. Gaia provides the best astrometric solution in the sky ever, so it tells us where all the stars are to incredibly high precision. It became operational basically as we were trying to solve this problem. We used the Hubble Space Telescope to take images of the object where we were getting on the order of 50 photons from this object in every image we took. Okay? 50 photons. It's a stupid number. Okay? And each one of those, we figured out where the center of light was coming from to approximately 1,000th of an arc second. Yes, 1,000th of an arc second, maybe 7,000th of an arc second, somewhere in that range. Ridiculously high precision. So we had to use Hubble to see it. We used the Gaia astrometry to make a reference frame, and then we used imaging from the CFHT to tie the Hubble images to the Gaia reference frame, because the Hubble images, anything that Gaia could see is saturated in any Hubble image. And so you take these images from the ground with the CFHT, and it provides kind of a ladder to get you between the two systems. And we managed to get the orbit in that way. Oh, and the other, oh yeah, so actually there's kind of more story here still. That was good enough to know where it was from Hubble, but really, that was still really wasn't enough precision. We really needed to get down to the 1 milli-arc-second kind of level of precision. And so we could do that if we could measure an occultation. So right, an occultation is when the object passes along the line of sight to a star. And there were a couple of stars that it was predicted that this object would pass close to. And so there was an international campaign deployed. Telescopes were sent to Argentina, to South Africa, to Senegal, and to Colombia to try to catch this occultation. The Colombia campaign was the most controversial one because it's not a very safe country to go off and visit. Interestingly, we had the U.S. ambassadors to Senegal contacted the Senegalese government, and the president of Senegal participated in the observation. He saw it as an opportunity to have science engagement for the citizens of Senegal. There's a nice article in the New York Times about the Senegalese occultation trip. Also, the Sophia is a telescope on board at 747 that the U.S. and German government operates. And Sophia was flown out into the path of the expected eclipse, or occultation, sorry, and tried to measure the occultation from on board Sophia. We missed the Sophia missed the event by about the wingspan of the plane, which, I mean, is really, really frustrating and so close, but there was actually, oh yes, it was actually even more weirdness to the story. So it turns out that all the astrometry is being done with Hubble Space Telescope imaging, like I described. And then you might remember there was an interstellar asteroid came by, Umama is what it's called. Then one came by, and it was, the world astronomy community was just very excited about it. Took a lot of images of it, including using Hubble. And they contacted the fellow who does our astrometry for Hubble for this target and said, could you do the astrometry for Umama? And he's like, sure, I can do that. So they gave him the images and he was doing it. And he kept getting a slight offset in the position of where the asteroid should be compared to where it was, and it was conflicting with other ground-based observations. So he couldn't understand where it was. So he went back into his software and found a sign error in an equation where he was adding a number he should have been subtracting. He changed it. Oh, wow, the orbit's exactly correct now. So then he went, well, I've been using the same software for the MU69 encounter. So he went back and reran it, and MU69 moved about the wingspan of a 747 at the time of the Sophia encounter because of the change in that software, this little adjustment, a term that long sign. It's very difficult to do a science experiment where you've only got one case, right? You have nothing to test your entire system against. So we're very lucky that that interstellar asteroid came by, so we could find that sign error because it was important to correct for the actual eventual orbit. Oh, so this is what the encounter looks like. So this line here, this is the orbit of MU69 or Ultima Thule, and its orbit around the sun. The sun's over here, and that's the shadow. And then over here is the spacecraft flying past and taking images as it goes along. Okay, this just kind of give you a bit of orientation for the images that we're looking at. Okay. What do we do here? We've got a spacecraft that's being tracked by the Deep Space Network, which is a set of large antennas all over the Earth. We attracted the Hubble. Then we actually were able to finally image it with New Horizons. There were really tiny differences between Ultima's position compared to where we thought it would be. And so a small correction, the course was made on December 18th. And then finally, on December 30th, we were able to take some downlink information. And we couldn't change anything about, all we could do was say, look a little bit to the left or look a little bit to the right of where you're currently planning. So a small change in the pointing and timing of the observations. If we had known how precisely we were going to hit this thing, we actually managed to get our time of encounter was off by a couple of seconds. I think it's a 2-point-something seconds, if I'm right. And the up-down error was a few hundred meters. Okay. So if we'd known that we were going to get that kind of precision, we would have taken more data. But instead, we have a lot of images of blank sky because as we were coming along with many, many, many pictures for 250 seconds before the encounter and 250 seconds after the encounter, just in case the math was wrong and it was actually somewhere in there. There's a lot of data with nothing in it. And there's actually a small debate going on right now about whether or not to download that data because it's expensive to get and there's nothing in it. Okay, so this is what it looks like from onboard the spacecraft. So watch the clock going on here. I'll rerun this again. Here we are, and this is the images. This is what you think your telescope's not doing great. This is a LORRI image. This is what they look like in raw format, okay? It's gigantic pixels with a little tiny telescope, and so it's very noisy. These are all stars, right? This is the galactic center we're looking towards. Then here it is with some processing to kind of smooth out the PSF, and there is MU69 popping out. When it first appeared in the first images, it was a little bit low in the pixel that it was supposed to be in. The center of the light was not quite in the part of the pixel we thought it would be. So we went back and looked at CFHT imaging that we had over the course of many years and looked at the stars that were in that same pixel. And one of the stars was getting brighter in the imaging. So we think actually the initial centroids were off a bit because there's a star right behind the source pushing the center brighter. And there it is there on December 10th, 11th, 13th. We can see that we go back to the very beginning, which starts in August. There's Christmas Day. Ooh, look how big and bright it is. Go right back to the beginning here. Restart. There we go. Right? There's nothing here. You can't see anything. There's that star getting brighter in the background. Anyway, so the goal is to map the geology and the morphology and to look for craters to kind of try to confirm the results from Pluto that there are no small craters. So we actually wrote a paper that we submitted in the days really before the encounter. We finished up a small paper predicting exactly how many craters there will be on this target based on the Pluto crater rate and our expectations for distribution of orbits in this part of the solar system. So hopefully we got that right. We're going to look at the map of the surface and the color composition, which we're all going to do here in just a minute, and look for ices. And I tell you, it's weird. There's ices on board on the surface of Pluto. And I think if you told the community, oh, we're going to see ice on the surface, there's no way you're going to see ice on the surface of a 10-kilometer sized object that's been sitting for 4 billion years, and it's all going to have sublimated away. You're just going to see this gooey, carbonated surface. I'll show you ice. Okay. So this is there's the target. There's where the spacecraft's going to go past. Okay. And so there's a lot of work done looking in this zone here for any indication of anything reflecting light that is dusty, kind of debris type material, because we don't want to run into it. And so right up until the 18th of December, there was this intensive search going on and a decision made that night about whether or not to risk flying so close to an unknown region of the solar system. And very fortunately, it was decided that we actually should fly that close. I was really worried that we were chicken out. Anyway. Because what are we looking for? So here's a comet CG that was flown past 2 years ago or 3 years ago. And so you can see this comet and it's rough surface and there's stuff sublimating off the surface. There's all this dust coming off. And so that was actually the worry is, if we don't understand the sublimation processes in the outer solar system, maybe there's dust coming off the surface of Alpha 2 that we just don't know what to expect. Probably not, but who knows? Okay, so this is the flyby. Okay, oh yeah, these are made by NASA, so they're all in lines. Here we have 40,000 miles out. We got the second best infrared image we're going to take. Okay, so then we started doing some color imaging. Way out here at 20-ish thousand miles, we get the best infrared data we're going to get. We took a color image here at about 10,000 miles out. And then here at between 5 and sort of 3,000 miles out, we have the best LORI images. And then we took a crescent image, and then we took this nighttime thermal image, which we didn't expect to get anything from with a shot. And then we start doing solar observations again. Okay, and each one of these little tick marks is 15 minutes of time. So in the 15, 30, 45 hour and 15 minutes before encounter, sounds like a great time to get the best image you can, except you're 40,000 kilometers away and you're going to get to it in 3. You can see this large band right here where we really just basically broke the bank taking images with the black and white camera because we didn't know for sure where is ultimately going to be. So we started taking images here and stopped here, and it was right there in the middle, exactly where it's supposed to be. Got a lot of these blank sky images. And then right half an hour after fly past, the mission's over. We can't detect this thing anymore. We can still, I think it's happening right now. We're currently taking images of Pluto from the spacecraft. We can still see Pluto. We can still detect it. We passed Pluto in 2015. We can't see MU69. We passed it in January. Okay, it's a really small object. Okay, here we go. December 30th. Science team's getting excited. We got our first resolved image of MU69. That's actually what it looks like from the spacecraft. And this is kind of there's a fellow who does image processing, Alex Parker, who's a grad student actually formerly here at Vic. And Alex makes these images. And so these are more artists' conceptions than they are real images, okay? Don't start interpreting anything about them. But people are, oh, look, it's kind of oblate shaped. There's some kind of, like, now that you know what it looks like, it's not a bad image. It's pretty good. Anyway, you can see these pixels. That's what we had. So this was an incredibly exciting moment to get those first images. And we also had that color data that I showed you before that was taken at a little bit lower resolution. And that's what that looked like. Oh, maybe I should turn the lights down. Yeah. There we go. There, that's great. So that is our third best color image of this thing, taken at about on December 30th. Pretty far out. So. And I'm going to next time I'm going to show you is what the science team looks like when they get to see this image. So, actually, you can see it's the slightly better. So this was the image that we got on January 1st. And this is basically our very first view of what it looked like. This is Stuart here. He's pretty good with Photoshop. And he managed to get he got the data processed the fastest. Everyone ran over and stood around his screen to look. This is Alan Stern, the PI for the mission. A couple of the other project scientists here all having a good gavel at our first sighting of Pluto. It really looked exactly like you think it should. I mean, it was a really weird experience of seeing something and saying, Yeah, that's exactly what I thought it was going to look like. And it explains so much about the nature of the solar system, because it's so perfectly round and small and binary. And those are three of the very fundamental things that we expected was going to be there. So this is what it looked like, that image from January 1st. So this is this round, big bottom part and this sort of smaller top part. We started to get an idea that maybe there was some impact basins here. We were confused about why this area here was so bright. We started looking at the torques and whether or not there was some tidal effect that causes this off the top to wobble back and forth to keep the material in the neck fresh. It's sort of odd. It has this oblateness, this not quite symmetric part. 30 kilometers across. In order for an object made of ice to pull itself into a roundish shape, it needs to be about 100 kilometers in diameter. So this thing is well below the threshold where something's pulling itself into a round shape. So this thing actually has no right to be round. It should just be whatever shape things were as they came together. It turns out things come together in a kind of a blobby, roundish shape, which tells us about the accretion process. Okay, finally we have the highest resolution color image, which I'm showing you in black and white because it looks a bit better in black and white color. And it's a 3-channel image. It's kind of an orangey color all across the surface. You have these two little eyes pointing at you. You start to see this giant trench here. Very strange. The very bright neck. There's a large impact basin here. There's some other topology overlaid on top. There are these mountains that are showing up. There's a chain of craters here. Look at this in a straight line. Right? You're looking for things. Random processes don't make straight lines. They don't make curves. There's a real physical processes going on. There's a giant trench here. I think this is kind of like a sad face. Yeah. Okay. It's got this sort of crushed in its head at the top. It's very flattened out, pockmarked with craters. And then there's these things like this, very bright, fresh looking things. But you can be the scientist. Look at this image and count for me the number of small impactors. A number like 0 is appropriate. Okay? The number that are easily visible on the surface is very low. We predicted there would be 30 small impactors on the surface of MU69. We may have been a bit high in our number. I'm not sure there's 30. There's probably close to it. Okay. That is, did it change? Okay, that's the higher resolution image. Okay, so that's the low resolution image with the color camera, and that's the high res image with the white light camera. So they're really very, and those are the two highest resolution images we have of the object. This is, a lot of what you see basically is, this one looks a bit better. I think the contrast is set better on this one than the display. It's going to crank up the contrast a bit to try to understand a little bit more. Okay, and this is what it looks like when we take that color image that was taken before encounter and overlay it on the optical image. And so another thing you can see here, and I'm going to emphasize this a bit more, is how uniform color it is. Okay, most of what you're seeing as color variations are actually not color, but intensity variations. So this part here is dark, but it's the same color as this part here. And this is light, but it's the same color as this part here. It's just getting brighter and darker, but it's not changing in color. And the color tells you about the chemistry of the surface. Okay, here's the spectrum of this object. That is ice absorbing. So that's the spectrum of MU69 from the spacecraft, and with possible detection of water ice, and pretty sure now also methanol ices on the surface of the object. And maybe even today, so it's in telecom, I think that's ascorbic acid. That's wrong. Anyway, we're really trying to understand like, all these little features, what's going on here with this bit that's coming in at 2.3 microns. That's indicative of a different organic absorber. We have this water feature here. We have some methanol features coming in. I'm trying to compare these these spectra to laboratory experiments to see if we can really disentangle exactly what the surface composition is. There's a meeting that starts on Monday in Houston where people will really I'm going to present the final interpretation here. Interestingly, as you go from here to here, right, this is the optical part of the spectrum, and we have no spectroscopy here, we just have colors. We just have measurements from the camera, so integrated photometry, and you can see that some of the, would seem to be that it's a little bit bluer, and it's a bit brighter in the blue than the comparison object being shown here, which is this object called Pholus. The Pholus is a little bit redder, as is this other thing, BE95. These are two objects that are in the Kuiper Belt centaurs, our solar system, and they have good spectrum. Here's an image that really tells the tale. Okay, so now we're just really kind of boiling it down to the scientific bare knuckles. And what's being plotted here is how blue is the object? Is it, or how red is the object, I should say? Is it really red, or is it only a little bit red? So blue here means that it's about as red as a dark red color. And red here means that it's really, really red. This is the slope of redness. So this blue end, there's a 20% slope per 100 nanometers. So it kind of is a bit gently towards the red. And this is 40%, so it's very steep towards red. So this basically means how red is it? And you can see that there's a very red place, and then there's this area here, which is quite blue, which it looks like this is maybe where some of the ice is coming from. And there's this feature here, and you can start to look and see maybe there's a ring here. There's this red spot here. The red seems to be associated with the basins of the giant impact basins, the giant impact basins being a kilometer or so across. This is probably just limb effect here. And we had a long debate about this. And again, Alex Parker, who made this image, Alex said he thinks that's just a data processing error that he's going to make go away. Okay, so that's the kind of detail that we're talking about this image with. But here's kind of like a brain dump of what it really means. So these are all the objects, are a large range of the objects in the outer solar system, from asteroids, satellites of the giant planets, more asteroids, Neptune Trojans, parts of the Kuiper Belt. You see we're getting, and as we go along here, these are blue things and these are red things. We're getting towards the redder and the redder and the redder and the redder end of these. And we can see this is the color distribution of this surface. So each one of these pixels is represented here as a point in this histogram, and we're really peaked towards the center of being around 34 or 32% gradient, which means that this is basically a very red object, consistent with being a red cold classical object, or in a high order resonance with Neptune, which it's not, so we know that's not the right class, but not as red as these ultra red things, which are the centaurs, like Pholus and BE95, which we showed you the spectrum. I showed you the spectrum a few slides ago. So a little bit less red than those, but very red. Very red basically means that it's been ice, it's been carbon processed or cosmic ray processed over the age of the solar system, and nothing much has happened to it. So there has not been a long history of bombardment of the surface. It's just sat there getting older and older. Okay, here it is. We fly into Alta. You can see that it's starting to, if you look at this for a while, you can start to maybe see some shape. You can see that it's not actually two spheres, right? There's something strange about the structure. But don't interpret that too much. This is what it looks like if you actually look at these images, to understand the resolution. Right. So the first images are taken from very far away, and as we get closer, we get better images. But this is what it looks like if you kind of make a model of the whole shape and then turn it around as it approaches us. And it looks quite flat, right? It looks like basically a flattened structure, maybe two donuts on top of each other, or something like that. Okay. Okay, so there's now this, we're trying to get close to using glasses, so now we take two images that are taken slightly far apart from each other and kind of blink them back and forth. So you can get an idea of this roundness to the object. This part here, this is a bit more round maybe, but this part down here seems to be exhibiting quite a bit of flattening. Okay, we can look at that just for a few minutes. Get an idea of the depth of these craters, with how much this trench is here. I don't know, this thing here. Okay. Now we're going to try the blue-green glasses. So here's the blue-green image. So let's try that out. Oh, I didn't bring my own glasses. Yeah. Is that working for anybody? It's a little bit hard to make. Okay, good. I'm going to get my glasses. Yeah. You can kind of make out that it's flattened out a little bit. If you look online, there are a few other stereo images you can look at. This is the only red-green one, the red-green one we've made. So some of you might be able to make out that this feature in the middle is quite flat. Okay? You can start to make out that the surface of the whole object is very flat in its presentation to us, which would then indicate that the other side is probably flat as well. Now, the initial reaction that most people have is, well, that doesn't make any sense. Normally, you look at the moon, you see that it's round, and we argue that it should basically be the same, all the way around. It's a sphere. And that would be true of everything you think. If you see a round thing in the sky, it's probably a spherical object. But we were looking for something we could actually detect with the telescope. So we needed an object that presented to us a very large surface area so that we could detect it. If everything out there is kind of a flattened disc-shaped thing, the only ones that we could detect would be the ones where the disk was pointing towards the sun. And so I think what we found is that the material in the outer solar system, when it forms into these little tiny planetesimal type shapes, it actually forms into a disc-shaped kind of structure. And then the ones that you would find are the ones where that disk is facing towards you. That's actually not inconsistent with expectations of some models of planetesimal accretion formation. So, okay, now I'm going to show you the close encounter image as it was taken from the spacecraft. This is the field of view of the entire field of view of the LORRI imager. The frame you see here is taken at this time, and the clock's going to count up as we look at more of these frames. Right on the screen. Here we go. Hi. That was the encounter. Up the screen here. Okay, this is taken at 5:27. This was taken at 5:26. 5:26:39. 5:27. Wow. 20 seconds a day. Each exposure is 1/10 of a second in length. I'm just showing you, if I could put them all together for you. Watch that one more time. Oops. Oh, here's another version. Oh no. This is going to just repeat. So this is actually right after the fly past, looking back at the silhouette of the object as you fly past. If you look at this, you can kind of make out that it's a flattened shape. So this edge here, that's just blurring, because the object's moving, the telescope's moving so fast. But we can kind of make out that it's not round. It has less depth than it should on the backlit side. It's not easy to make out, but it is there for you to see. So what we can do is we can try to map. This is the image. We try to map out basically what the shape is. And this is what we thought we were going to approach. But after analyzing the data and looking at it very carefully, it probably looks more like this, where the sort of uncertainty on the shape is given by this. It's at least this thin, and it may be as round as that. So it might be kind of that aspect ratio. This thing could be still somewhat spherical, but it's definitely not two round objects touching each other, which is a little bit odd. Right? They're both quite flattened. And so you can say, well, why, one flattened thing with a round thing on top, that would tell you that, okay, both are equally likely. But two flattened things that happen to come together like this indicate that, well, making flattened things is pretty common. So there's, whether or not this is round, there's going to be a lot of time spent looking at this image, this data set here. Sorry, try to decide, is that a round thing or not? So a lot of people looking at the stars as they disappear and trying to see exactly what the shape of that silhouette is. Fun times. Yeah, here it is. So this is what it would basically look like as it moves. Okay, that's our best idea of the shape at this point. Which really unusual shape. So I think we're going to learn a lot about how planetesimals accrete and how this process of initial starting planet formation works by trying to make things that will produce this kind of round flattened thing. And that's basically where the story of MU69 sits right now. And we're really working on basically putting together the pieces of this puzzle of planetesimal formation and seeing how all of this basically, how do you go from these models of planetesimal formation to make this. Thanks a lot. Oh yeah, that's right.
Well, that was amazing. Thanks so much, JJ, for that. I'm sure there's plenty of questions out there. Yes?
Were you able to find out anything about composition or density?
The density is a tricky one because certainly the gravitational forces of the object were too low to be detected by the spacecraft. It has a very low spin period. This object's only rotating at about a 17-hour spin period. And normally objects that come together to form a contact system, they have a spin period which is really close to their orbit period prior to contact. And if this object has a spin period that matches its orbit period, and it's spherical, then it has to have a density that's around 0.3 grams per centimeter cubed, 0.3 grams per centimeter cubed. So 1/3 the density of water, which is stupidly low. So that's probably not the density. And as we see, it's not quite spheroidal. And if we kind of assume it's a bit flat, we can get the density all the way up to 0.5 gram per centimeter cubed, 0.5 grams per centimeter. Which is still too low. And so probably it's a very porous object. The density is probably around 0.5 gram per centimeter cubed with a lot of porosity. And now we're doing thermal modeling to try to understand how that porosity might flow.
Put all the water, where does that come from?
So the
Why is
water,
it there?
right. So we knew there's water in the outer solar system. Water ice, H2O molecules out there will freeze. That's 25 Kelvin. So no problem with that. The problem is they also sublimate, and they also cosmic ray bombardment would obliterate them from the surface. So there's going to be a fair bit of trying to model the particle environment to understand if you can actually preserve water ice on the surface, or do you have to have it delivered exogenically, or is it recent bombardments causing refreshing of the surface? So exactly why there's water is a bit of a mystery. Okay.
Yeah, I've heard the Victoria High School astronomy department's been working with you. I was just wondering if you could tell me a little bit about what they're doing.
Sure. So we're actually just getting started. So I'm running a program, some of you may know about, called, we're calling our part of it CanCon. It's called TNO Recon. So TNO Recon is a project run out of Boulder, Colorado, funded through the National Sciences Foundation. And NRC in Victoria is also funding a small Canadian extension, CanCon, at a very sort of economical rate. So what we're doing is we're, the initial phase, we bought some small telescopes. They're 12-inch dogs, and some really nice high-speed GPS-enabled CMOS cameras. And we've delivered 3 telescopes and 4 cameras to schools in the Okanagan Valley. So Penticton High has a camera. They have their own telescope already. A school in the Soyuz has one. A school in Oliver has one. And in April, I'm going to a school in Kelowna to deliver one. We also have one at a school in Vernon and a school in Kelowna, Vernon, Summerland. So Summerland, Penticton, Oliver. And then actually, some of you may know Peter Servolos and Deborah. And so they're actually participating as well because they have their own observatory and Peter bought his own camera. So we have, I think, 8 telescopes. What we do is they're on a sort of a line going up north-south, starting from the US school starting in Southern California. They go all the way up to the border with BC, and then we have these 8 telescopes extending up towards Vernon. And we predict a possible occultation event of a Kuiper belt object occulting a star. And then we observe that event with those telescopes. And the predictions are really quite rough because the orbits of, we don't know all orbits of Kuiper belt objects as precisely as MU69. And so the uncertainty is about 1,000 kilometers. So if we can get telescopes that occupy a 1,000 kilometer line to all look at the occultation event at the same time, we're pretty sure one of them is going to see it. And so we've recruited high schools along that corridor to participate. I've recently gone out to Vic High, and they've agreed to participate in this project. And we've purchased another camera, and we're going to mount it on the 16-inch up at the observatory. And we're going to participate in the occultation events from the observatory there, if I can get the telescope and the camera working together properly.
When's this going to take place?
So we're actually, we do predicted occultation events. And so the goal is to have 3-ish events per school term. And the next event will be, I think it's on April 24th or April 26th. And so I have to get the camera working on the 16-inch before.
What are the cameras and the GPS that you use?
Okay, so the precise model is the QHY174M GPS. And the reason we're using that camera is because we got in touch with the manufacturer, QHY, when we were doing the NU69 occultations, and talked them into making an occultation camera that we used on that campaign. And in exchange for that, if you go to QHY's website, they talk about their fantastic New Horizons occultation camera. And they're really happy to manufacture this really beautiful camera. It's a bit expensive. It's about $1,600 US for the camera. But it reads out at about 40 hertz, has almost no read noise, and the GPS signal is injected right into the images headers as they come off.
So this is the point gray camera that was used for a previous occultation pattern?
No, this is purpose designed for this CanCon TNO Recon project.
So it has all the, finds the GPS.
It has the-
information.
Yeah, it has the GPS geotagged and time tagged in the header with the image as the images are written to the disk.
So each image is encrypted.
And it records.
In the header. And it records it as a FITS image, which is a sort of astronomy standard for research astronomy. So it records a binary file format and uses a piece of software called SharpCat, which is distributed by a different person, but in collaboration with QHY. The timing in the tags with the GPS signal is good to a microsecond. So, which is much better. The occultation events last for 3 or 4 seconds. So microsecond timing is sufficient.
Hey, JJ, I've got a general question about your mission. It's not very often a person finds himself in the glaring spotlight, and you were in that. I just wondered if you could share a few thoughts of, was that stressful to be in that position, or is it exhilarating, or?
Well, you know, retrospectively, you can look back on all the things that led up to making it possible to have this encounter happen, and all the good fortunes that had to have occurred, and just kind of think how many places along the way things could have gone off the rails. And so it was very satisfying to get to that point and realize, well, everything has worked out through the various supports and processes. So that was very gratifying as I think about the way science works and the way our society works. The actual event itself, I'd say, it's actually been overwhelming. I've not, there's these 50 scientists or so that are working on this project. If you imagine that each of us has an idea every half hour and emails the other 50 scientists. It's kind of what's going on right now, okay? So I've actually I actually changed email addresses for social and work purposes, and just all the email from this team goes to the Gmail address that I can't even keep up to now. So it's a bit overwhelming. I don't understand. Alan Stern, who's the PI of the project, I have no idea how that guy is still alive, because he responds to people's ideas within minutes of them posing them, regardless of the rate at which they're posed. But even for him, it overwhelmed him. And I think 3 weeks ago, he was actually became quite ill from the stress. So I had to take a little step back. Yeah. Super excited.
One more question. Sure. Was there any consideration to slow the spacecraft so we have more time to collect the data?
We did slow it down.
It went so fast.
So we could have slowed it down by another 1 or 2% if we burned every last sort of ounce of fuel on board. Unfortunately, the spacecraft doesn't really have a lot of fuel on board for doing much in the way of velocity changes. And we didn't want to do that because we wanted to have the possibility for the Kuiper extended mission.
So what's the next stage and next project?
Unfortunately, the Kuiper belt is a little bit thin out there, and so there probably won't be another close encounter. I say probably because we hold out faint hope, and we will keep trying, but right now, it looks like what we'll be doing is observing more distant Kuiper belt objects. So things that the spacecraft can still detect, and we can make really unique observations where the sun is here, the object's here, and the spacecraft's here, and so we're seeing this high phase view of the objects. Normally, for things out past the orbit of the Earth, it's very difficult to get high phase observations. And high phase observations tell you about the cratering or surface roughness and albedo or reflectivity of the object. Where we think we might be able to do a small survey and measure those aspects. So in fact, I just finished asking the Canadian Space Agency to fund us here in Victoria to find more things to look at with new horizons. And we'll see if we get the funding to make that possible.
Okay, well, you've been very generous with your time. It sounds like you're crazy busy, and we really appreciate this. And I think I'm very excited about everything that's happened here. So As a token of thanks, we have this.
Great, oh, yes. Glad.
So thank you very much. Before we hit the astronomy lab, I just want to quickly go over some of the upcoming events. Besides the Astronomy Cafe, our next council meeting is next Wednesday, the 20th. And then there was talk, Bruce Stammer on the 25th, and Karoon sent me this. And basically, it sounds like it's going to be an interesting talk. It's in the Engineering and Sciences Room 116 at 7 p.m. on Monday, March 25th. And you don't need to register, so please keep that in mind. Karoon knows this person and recommended the talk. Also, we have, I believe the Messier Marathon is scheduled for April 6th. And Rask's own Ellen, for the fellow from the Okanagan, he wrote an article in the latest Sky and Telescope magazine about how to optimize your chances of picking off more Messier Marathon objects. Check that out. We also have the Vancouver Island Regional Science Fair, Sunday, April 7th, and they still might be looking for judges. So if you were interested, you might want to contact Dorothy Paul about that. The next monthly meeting is on April 10th. We have a UVic observing session on the 12th. Dorothy's involved with an eco-literacy event at one of the elementary schools on the 13th. And then Astronomy Day on the 27th. So plenty of stuff coming up in the next month. And then we just got this, National Geographic is doing something at the Royal Theatre. I think it costs about $30 a ticket. There's a 20% discount if you're interested in going to this. Contact me if you'd like to go to this. It's with a NASA engineer who is very active with the cameras on this thing. It might be a real good opportunity to learn a bit more about Mars. So, and with that, the only other thing is if you're interested in getting one of those books on Explore the Universe, I wouldn't approach me. I'd go see Nelson. He seems to be able to sell them better. Thanks very much, everyone.